All right, so to end this unit, we're going to talk about integrals that result in inverse trigonometric functions. And this is directly coming off of our previous lesson where we found the derivatives of inverse trig functions. So if you haven't watched that video, make sure you watch that first before we dive into this lesson. So in our previous lesson, we talked about finding the derivatives of inverse trig functions. So we saw why the derivative of arcsine of x was something like 1 over the square root of 1 minus x squared. So it makes sense then that we could just simply reverse these derivative rules to come up with the basic rules for integrating. That is to say, the integral of 1 over root 1 minus x squared clearly would have to be the arcsine of x, or the inverse sine of x, plus some constant c. And the integral of something like 1 over 1 plus x squared would have to be arctangent of x plus c. And we could keep going along down the line with this and say something like the integral of 1 over the absolute value of x root times root x squared minus 1 would have to be the arcsecant of x plus c. And you'll notice too that I'm only writing out the rules for sine, tangent, and secant. And the only reason why I'm only listing these is because the other three functions, cosecant, cotangent, and cosine, are simply going to be the opposite sign versions. And again, if you watch the previous lesson on this, you'll understand why arc cosine's derivative is simply the negative of, or the opposite sign of arc sine. So you can go and watch those. So I'll just write that. The cofunctions are simply are just the negatives, or the negative versions, if you will. All right, we can just factor out a negative. Now, it would be great if all of our integrals were just simply 1 over root 1 minus x squared. Or that is to say, they seem to be directly the result of differentiating arcsine of something like just x. But as often is the case, our functions aren't simply just going to be x. That is to say, we can't always just draw something, or our triangle, where the sine of some angle y is x over 1. We often have many situations where our functions are a little bit more complicated than that. So we want to make sure that we have another integration rule to deal with such cases. So I'm going to go ahead and I'm going to derive the rule for integrating something like the arcsine of u over a. Okay? And you're going to see that this process is pretty similar to what we've done with deriving the rules for differentiating these inverse trig functions. So the first thing that I want to point out here is that if we are differentiating arcsine of something like u over a, this is equivalent to saying we're finding the derivative of the sine of some angle y results in the ratio u over a. So something like this, okay? And let me take a moment here just to draw what that triangle might look like. So if I had something like this here, okay, we can say if this is my angle A, the sine of my angle A is opposite over hypotenuse. So this opposite side is u, and my hypotenuse would then have to be A. And using the Pythagorean theorem, we can say that this adjacent side here would have to be the square root of a squared minus u squared, okay? So we're going to leave that here. We're going to come back to this in just a moment. But if we're differentiating sine y is equal to u over a, I'm going to just also rewrite this. I'm going to just say this is equal. I'm going to rewrite this. I'm going to just move my denominator a here to the other side, which is going to just make my life a little bit easier when I'm differentiating. So I'm going to implicitly derive this here. I'm going to say that this is equal to, well, a is just some constant. The derivative of sine is cosine of y times y prime, since we're implicitly differentiating with respect to x. And the derivative of u is just going to be u prime. Now to isolate y prime, I'm going to say that this is equal to u prime over a times the cosine of y. And we don't want to just leave it as cosine of y. We want to rewrite that in terms of x. So we're going to say this is u prime all over a times the cosine of y. The cosine of this angle is root a squared minus u squared all over a, which we can then simplify easily to just u prime over root a squared minus u squared. And by finding the derivative of arcsine of u over a, we now have a situation here where then if we can see this structure, if we can see the denominator consisting of some constant where a is some constant and u is some function, And the derivative of u is in the numerator, and we see that the denominator is root a squared minus u squared. This then has, if we integrate this, this has to result in arcsine of u over a plus c. So by actually finding the derivative of the arcsine of u over a, we're able to come up with a rule for integrating something whose derivative results, okay? So if you want to right now, you could actually pause the video and derive the rules for arctangent and arcsecant. If you feel like you got it, you can go on to just writing down these three rules and memorizing them and starting to work on the problems below, but I'm going to really just quickly derive the other two so we can see why our rules are what they are, okay? So I'm actually going to go to the arcsecant first. Let me actually make this a little bit smaller. Let me go to arcsecant first because we're just gonna go in order as to how they're listed in the summary. So let me just switch my colors here. So let's go to arcsecant. So what would this one look like? Well, this is equivalent to saying the derivative of secant of y is equal to u over a, which again, I'm going to move that denominator over to the other side and write this a and write this as u here. And again, I can draw that triangle here as such, where I would then say the secant of angle y, which was u over a, so our hypotenuse over our adjacent, and this side here is u squared minus root u squared minus a squared. So to differentiate this, we would then get, this would be a times the derivative of secant, which is secant y, tangent y, times y prime, and all of this is equal to u prime, u prime, okay? So then if I isolate y prime, I get u prime over a times secant y, tangent y. Well, what is secant of y? Secant is hypotenuse over adjacent, so a times u over a. That was already given to us here. And then tangent of y is opposite over adjacent. And if we clean this up a little bit, we notice we have u prime all over u times root a u squared minus a squared. And this constant of a here, I can move to the numerator. And what you will see is that when we are coming up with the rules of integrating, what we're looking for, compare this with what we have here. All we're missing is that a. And we know that we can always multiply by some constant of a as long as we have the reciprocal of that constant there as well, which we can often move out, which is where this 1 over a comes from in our rule for integrating this structure. So if we can see the structure of a times u prime over u times square root of u squared minus a squared, then that's simply going to be 1 over a times arcsecant of the absolute value of u over a plus c. And again, if you're not sure where we get the absolute value from, again, watch my lesson from yesterday or my previous lesson, and that'll hopefully clarify where we're getting that absolute value from. Okay, and a lot of times too, just keep in mind that we may not see that a or that constant of a in our integram, but it's easily introduced by just multiplying by a and also multiplying by the reciprocal. Okay, all right. Hopefully we're getting this right by now. I'm going to do one more. I'm going to just do the arctangent one right over here. Let me just quickly do this one. This again is, hopefully we get that by now. We can easily say that this is equal to finding the derivative of a times the tangent of y is equal to u. And if I want to draw a triangle here to represent this, we can say that if this is y, tangent of y is a over u, in which case this is u squared plus a squared, okay, which we're going to use in just a moment. The derivative of a tangent y equals u. If we implicitly differentiate that, that's a times secant squared y times y prime is equal to u prime. Isolate y prime. And then secant squared y, that's going to be root u squared plus a squared all over u squared, or excuse me, a squared, I apologize. Oh, I switched these around with my triangle, I apologize. This is why I was getting confused. All right, so this is going to be all over a this squared, which this cleans up nicely to u prime over, let me write this here, u prime over a times u squared plus a squared over a squared, which if we divide this out, we get again a times u prime over u squared plus a squared. So this is how we get the rule for the arcsecant. And the same kind of deal, if we don't see that constant of a in there, we can introduce by multiplying by a as long as we multiply by 1 over a as well. Okay? All right, so now that we've spent quite a bit of time actually deriving these rules for integrating functions that result in these inverse trig functions, let's actually do some practice problems with this, okay? So I'm going to let you kind of pause the video right now if you need to, again, jot down these formulas, write down these problems, and I will work through a handful of them, which I think to be the most important here. Okay, so I'm going to just run through these. Feel free to pause the video as you go along if you feel like I'm going a little bit too fast. All right, so let's work on this first one. Well, hopefully we see here that this is my constant a. So that is to say, I can rewrite this if it helps at all as the square root of 2 squared minus x squared, where a, this is a squared. So that means a is equal to 2 here, u is equal to x, which means the derivative of u prime, is just equal to 1. So here's my u prime. And what do you know? That seems to match up perfectly with the arcsine. So we can say that this is simply the arcsine of u over a, which is x over 2, all of that plus c. Okay? All right. What about something like number 2? Well, number 2 here, again, I can rewrite this, and I don't need to rewrite it. Hopefully you can just identify it, but if it helps you see it better, this is equivalent to 2x plus, or 2x squared plus 5 squared. In which case, again, this is u, this is a. So what formula does this seem to match? Looks like it matches pretty nicely with arctangent, except I would need u prime, which is equal to 2. So I can easily introduce a 2 by multiplying by 2 here, so long as I also multiply by 1/2. So this would give me 1 over 2 times, now we can actually integrate, 1 over 2 times, we see hopefully that we're doing arctangent, 1 over our a value, 5, okay, 1 over a, times the arctangent of u, 2x over 5, all of that plus c. Okay? All right, number 3. Well, this one here, we can see that this is equal to the integral of, well, we're going to rewrite it this way. This is going to be 4 times 2 all over root 3 squared plus 2x squared dx. Again, this is my u, this is my a. My u prime would have to be 2, so this is my u prime. So I can then move that 4 to the outside. And what I have is 4 times u prime, or 4 times u prime over a squared plus u squared, or the integral of that. So this is going to be another arctangent. So this is 4 times 1 over root 3. So we can just actually write that as 4 over root 3 times the arctangent of u over a plus c. Okay? All right. How about something like number 4 here? Well, at first glance, number 4, we might think to just rewrite this so that it's the following. In which case, this is u, this is a, and u prime would have to be equal to e to the x. Well, I don't see an e to the x here, but that can be easily introduced by saying times e to the x up here, as long as we also multiply or divide by e to the x. I'm not changing the value of my integrand at all. And so now actually we see here, this is my u prime, and here is my absolute value of u. The absolute value of e to the x is just e to the x. So this is an arcsecant situation, right? And so we can see that this is going to simply be the arcsecant of e to the x plus c. All right, what about something like number 5? Number 5, just as a hint, you're going to want to complete the square. Why is that? Because I don't have any square roots in the denominator, but if I can set this up where this is 1 over, or u prime over a squared plus u squared, then we have an arctangent situation. So I can write this as x squared minus 4x plus what value would I need to complete the square? And the answer is, I would just need a 4 here. Well, do I have a 4? Sure I do. I could just borrow a 4 right from that 7. So rewrite the denominator such as that, dx, which is equivalent to 1 over x minus 2 squared plus root 3 squared. Here's my u, here's my a, My u prime is just going to be 1. So I can say that this is 1 over root 3, or 1 over a, arctangent of x minus 2 over root 3 plus c. Okay? All right, next one, number 6. Well, here we can identify this as this being a squared. This here is my u squared. U prime is equal to cosine of x. So here's my u prime. So this is just really simply, again, another arctangent of u over a, where u is equal to sine x, a is equal to 1, so I don't really need to write it. And this integral now evaluated at pi over 2 and 0. So the arctangent, well, I don't think I need to even write that. Sine of pi over 2 is equal to 1. So this is going to be the arctangent of 1 minus the arctangent evaluated at 0. That's pi over 4 minus 0, and that's pi over 4. Okay. All right, number 7 right over here. This one, it'd be a good idea to actually divide the numerator by the denominator. And what we get here is this is x cubed plus x. Subtract all this, we have negative x. So I can then rewrite this integral as x minus x over x squared plus 1. And this is actually pretty easy to integrate. In fact, this one is one that doesn't require inverse trig functions at all. The integral of x is x squared over 2. And the integral of x over x squared plus 1, well, this is actually an integral that results in the natural logarithm, where this is our u, and this is our u prime, provided that we have a negative 2 here. If we just had a negative 2, or 2, I should say, which we can then introduce, so we would say plus minus 1/2, the natural log of absolute value of x squared plus 1 plus c. There's my integral there. All right, last one, number 8. This is a good practice problem. In fact, there's a couple of good things going on. Pause the video again if you haven't been doing so as we go along. This one can be broken down as, we're going to split this up actually. We're going to split this up as in 2 separate integrals. So for the first one here, if I integrate this integral here, if you look at it, this can be just done using the reverse chain rule here. So we can actually say that this is, let me write this here, this is x over root 4 minus x squared dx. So as long as we had a negative 2 up here, because we have our u, which is 4 minus x squared, being raised to the negative 1 power, then this would just be negative 1/2. Right? So that is to say, if we wanted to use this in terms of chain rule, which you don't have to, but if u is equal to 4 minus x squared, right, we have u being raised to the negative 1/2 power. And what is u prime? We would need the negative 2 then there. Okay, so, but we could get away without having to write any of that. In which case, now this is just going to result in, and I'll just write the result of this here, negative 1/2 times 2 over 1 times 4 minus x squared to the 1/2. So there's that. Now let's do this next integral. We have all of this here. Well, what is this result here? Well, I can say plus 2 times the integral of 1 over root 4 minus x squared, and this now looks like something that will be an inverse trig function. And it is. This is actually arcsine. So we can say this is plus 2 arcsine of x over 2, u over a, all of that plus c. And if I wanted to clean that left side up, negative 1/2 times 2, that just gives me negative. Anything raised to the 1/2 power is just the root. You could leave it as 1/2 too, but that might just make it a little bit easier for you to see. All right? Okay, so hopefully we're getting some of these rules a little bit better. And yes, this stuff is tricky. There's quite a bit that we have to remember. And the challenge is going to be looking at an integral and trying to identify the structure. But I assure you, just keep working at it and it will come. All right, hopefully this lesson helped out.